Now, before starting with the proof, which one from among the theorems that we have seen so far do you think will play a major role in proving that Rnd is a complete space? Now, what we'll do here is we will start with the Cauchy sequence and then show that it's convergent. What are the theorems that deal with the existence of convergent sequences, what happens to their limits, and so on in Euclidean spaces?
Closeness?
Huh?
Closeness, maybe?
Well, closeness, but that's not a theorem. That's a concept, and well, it's related to the limit of any convergent sequence belonging to the set. That might be part of this as well, but Bolzano-Weierstrass theorem was, well, it said if a sequence is bounded, then it has a convergent subsequence. So what we'll do is we will start with any Cauchy sequence in this space, show that it'll be bounded. Well, by Bolzano-Weierstrass, it will have a convergent subsequence. Well, but we need the convergence of the sequence itself, but the conjunction of the existence of a convergent subsequence and the sequence itself being Cauchy, that will actually imply that the sequence itself is convergent and, in fact, converges to the limit of the subsequence. Okay? So, well, then, we have the agenda. So let Xn be any Cauchy sequence in Rd. If the agenda works, then the first item is to show that this is bounded. But we know that it's a Cauchy sequence. Well, that means whenever we take any positive real number epsilon, there will be a point in the sequence such that from that point on, the distance between any two terms in the sequence, that will be less than epsilon. So from that point on, in fact, the sequence will be bounded, no matter what epsilon we take. But the first part, well, that will be finite, no matter how large the number of terms in that initial part is. Well, if it's finite, and if we just take the distances between all 2 points in that finite set, well, that will have a maximum. Well, the only thing might be, what if we take some point from the finite initial segment and some point from the tail? But you can see via the triangle inequality, we will be able to show that that's bounded as well. Well, since epsilon was not important, let's start by taking any particular epsilon. Well, if we do that, we usually take a simple number, and the simplest positive real number, that's 1. So set epsilon equal to 1, that will be positive. Now there is, say, some natural number k such that no matter what 2 points in the sequence beyond that point, represented by cap k, I take, then the xm xn, that will be less than 1. Now, let me consider the initial segment. Now, the set. Here I will take all distances between xk and xl, where k and l are natural numbers, but this time they both are less than or equal to k. This set will be finite, so its maximum will exist. It's a finite set of reals, is finite, and non-empty, of course. So that, let me give a name to that maximum, L equal to the maximum of the xl xk, such that kl in n, with both of them being less than or equal to cap k, that exists. Now that exists, and that will be something non-negative. But now, since I also wish to find an upper bound for distances between 2 points, one of which is in this initial segment, and the other is out in the tail, well, then I'll use the triangle inequality. So let me take the sum of this bound for the tail and this bound for the initial segment. So set m equal to L plus 1. Now we claim that this cap m, which is a positive real number, is an upper bound for all possible distances between any 2 points in this sequence. Well, then take any 2 points, that is, take any KL in N. Now there will be 3 cases. Case 1, both K and L, they're less than or equal to cap K. Now, the distance between these, that will be less than or equal to L. This belongs to the set whose maximum is L, and that's less than M. So for this case, we have the desired result. Case 2, well, K and L might both be larger than or equal to cap K. In that case, we know that here this will be, well, in fact, less than 1, and that will be less than or equal to M. Well, we are done in this case as well. Now, case 3, K is less than or equal to cap K, and L larger than or equal to cap K. Now this time we have dxk, dxl. Now what I know is x lowercase k and x uppercase k, they are both in the initial segment, so their distance is less than or equal to L. But if I take cap K and L now, well, the distance between those, that will be less than or equal to 1 because they both are in the tail. So I take as the intermediate point just the point on the boundary, x of cap K. So this will be less than or equal to dxk x cap k plus dx cap k xl. Now this will be less than or equal to L, and this will be less than or equal to 1. So this will be less than or equal to L plus 1, which is M. Well, let me write case 4. If we have K larger than or equal to cap K, L less than or equal to cap K, well, the same will hold by interchanging the roles of K and L here. XL less than or equal to M. So, the set of all terms in this sequence, this is bounded. Because they are all large, this is bounded. Between any 2 points, the distance between them is less than or equal to M. But now by Bolzano-Weierstrass theorem, Xn, we are in a Euclidean space. Bolzano-Weierstrass was not true in general in metric spaces, but we're in a Euclidean space. This has a convergent subsequence X sub R sub n, where X sub R sub n converges to A for some A in Rn. I took Rn, okay. Now, as we have noted, well, that's fine, but we're interested in showing that the sequence X sub n itself is convergent. But we know 2 things now. It's a Cauchy sequence, and there's a subsequence which is convergent. So we'll conjoin them to get the result. Now, to show that Xn is convergent and actually that it converges to A, well, let's use the definition of convergence and let's take any epsilon positive. Let epsilon be positive. Now let us spell out in detail what we can conclude from the 2 facts just mentioned. Now there is some, say, K1 in N, such that for all N larger than or equal to K1, the distance between X sub Rn and A, that is less than epsilon over 2. Why epsilon over 2? Well, we'll use the other half of epsilon for Cauchy, for the conclusion that will follow from the fact that it's a Cauchy sequence. And there is some K2 in N such that for all Mn larger than or equal to K2, we have dxm, dxn is again less than epsilon over 2. Well, we wish to be in a region where both of these hold. So, well, let's take just cap k as the maximum of k1 and k2, so that when n or m and n are larger than or equal to that, both of these conclusions hold. Set k equal to the maximum of K1, K2. Well, then what we expect is whenever n is larger than or equal to cap k, then the distance between xn and a will be less than epsilon. Now, for any n, in n with n larger than or equal to k, consider xn a. But in order to use these both, now here I have n, but I need something else. But that something else, n, that should be chosen in such a way so that for that something else this holds as well. So that something else, that will be r sub cap k. So this will be less than or equal to dxn x sub r sub cap k plus dx sub r sub cap k a. Well, will this r sub cap k larger than or equal to cap k? Yes, by definition of a subsequence, well, we took an increasing sequence, an increasing subsequence of the sequence consisting of natural numbers. So this is larger than or equal to k. So n and this number, they are both larger than or equal to cap k, thus larger than or equal to k2. So this will be less than epsilon over 2. But since cap k is also larger than or equal to k1, this will be less than epsilon over 2 as well. So this will be less than the sum of these, which is epsilon. So xn converges to a, so xn is convergent. Thus, R and D is complete. When we come to optimization results, well, that will happen at the beginning of next semester. I advise you to go through the following test. The claim is that we are actually taking the shortest path to those optimization results. It will be difficult to find some result which is considered in this course which can be discarded, which can be taken out if we wish to prove those optimization theorems. So this is, in a sense, the shortest way to that, to our major aim. Okay. Next, we have the notion of a subspace of a metric space. So we're interested in when the completeness pertaining to the large space or pertaining to the subspace, what that implies. Now, we in general know if a space is complete, then that does not imply just that. That does not imply anything concerning the completeness of the subspaces. Where do we know that from? RD is complete. What about QD? If we take as the subset the set of rationals, well, we have seen that that's not complete. Well, in fact, if you take r minus qd, that's not complete either. But here, okay, so we'll have two results. But we also have the intuition that, well, closedness possibly will play some important role, because if you have a convergent sequence, then its limit will belong to the set if that sequence comes from a closed set. Now here, let x, y be non-empty sets with y being a subset of cat x, and rho a metric on x. Thus, its restriction is also a metric on y, and y rho, that will be a subspace of x rho. First, if the subspace is complete, then what topological properties do you think will y possess in the large set x rho? Can it be not closed? No, that does not seem to be possible, because in that case, well, a Cauchy sequence you would have some sequence which is convergent in the large space, but such that the terms come from the smaller set, but the limit does not belong to the set. So if y rho is complete, then what we expect is y is a closed subset of x. Secondly, if x rho is complete, and y is a subset, is closed in x with respect to rho, then this will imply that y rho is complete as well. Now here, the proofs of the two statements are similar, so I'll prove one and I'll leave the proof of two as an exercise to you. So let's assume that y rho is complete. Then we wish to show that y is a closed subset of x, but completeness is defined in terms of sequences, and we have a characterization of closedness of a set in terms of sequences as well. Well, to show that y is closed, it might be useful to use that characterization. So we'll take any sequence xn be a sequence in y such that xn is convergent in the big space in order to conclude that cap y is close, we need to show that A is in cap y. That's all we need to show, okay? Okay. But what do we know? a convergent sequence is always, in any metric space, a Cauchy sequence. Now, Xn is a convergent sequence in X row, so it's a Cauchy sequence in X row. Now, Xn is a Cauchy sequence in X row. But all the terms of Xn, they belong to cap Y. So it's a Cauchy sequence in Y row as well. Because the definition of a Cauchy sequence, well, given any epsilon, there's some place such that according to rho, the distances of any 2 points beyond that place in the sequence, that's less than epsilon. That holds, okay. As Xn is a sequence in Y, Xn is also a Cauchy sequence in Y row. What do we know about Y row? It's complete. So this must be convergent in Y row. As Y row is complete, Xn converges to some B for some B in Y. But what do we know about limits of convergent sequences? Well, they're unique, so A and B must be the same. But then B is equal to A. So we have shown that if we start with any sequence in Y such that it converges to some point in cap X, that limit, that must belong to the set cap Y, but that's nothing but saying that cap Y is closed. So Y is closed in X with respect to rho. Well, that left you as an exercise. Now, we will consider now whether our conjecture concerning total boundedness and closedness holds in complete spaces. Remember, closed and bounded, if and only if compact, that was true in Euclidean spaces, but not so in general metric spaces. But then we asked the following question: is it possible to actually modify the notion of boundedness in such a way that the new primed boundedness is equivalent to boundedness in Euclidean spaces, but in metric spaces, it yields the theorem that a set is compact if and only if it is closed and totally bounded. Well, then, we took that modified version as total boundedness, but we have seen, that the extension of Heine-Borel by replacing boundedness by total boundedness, that was not valid in general in all metric spaces. But now the question is, will that be the case for complete metric spaces? And that will be the case. Now this is the climax of all this section. Theorem. Let X rho be a complete metric space and K a subset of X. Now, K is compact if and only if K is closed and totally bounded. We in fact know half of this theorem to hold in general metric spaces because we have proven that compactness implies both total boundedness and closeness in any metric space. We already know that K is closed and totally bounded if K is compact. In fact, without using the completeness. Now, in order to show that the other direction holds, let's proceed by contradiction. So let us first assume that K is closed and totally bounded. Now let us suppose that K is not compact. Well, then this means, if we just use the definition of compactness, that there is an open covering, say script G, of K, which has no finite subcovering for K. Now let me note that down as well. Well, then there is some open covering script G of K, which has no finite subcovering for K. This should lead to a contradiction. And here we know that we have to use completeness. Well, if we have to use completeness, then somehow, somewhere in the proof, we should construct a Cauchy sequence and using completeness, deduce that it's convergent and that its limit belongs to the set and do something with that. Now, first, a pictorial agenda. And then we'll translate the picture to a formal language. Since K is totally bounded, it's bounded in particular. So I can find actually a large ball about some point which entirely contains K. In fact, I can take this X naught in cap K as well. Well, cap K, can it be empty? No, we suppose it's not compact. The empty set is compact, so it will not be empty. In fact, it should have an abundance of members. It cannot be finite either, because it would be compact. Well, then, what I'll do is, I'll choose some other point x1 in K, with half the radius and satisfying the following properties. Now this will have some radius cap m. This will have the radius cap m over 2, because I'm trying to construct the Cauchy sequence. Each time I will take half of the previous radius. This will be in cap k. x0 and x1, they're candidates for being the first two members of the sequence I'm trying to construct in cap k. But now I have to make use of somehow that this is not compact. Now, for the first big case, K cap K is entirely within that set. So script G has no finite subcovering for the intersection of cap K with the large epsilon ball, because it's cap K. But if I can choose x1 and this in such a way that script G still has no finite subcovering for the portion of cap K which stays within here, and well, I will take the second ball in such a way that it actually has a non-empty intersection with the previous one. Well, for this it's clear because, well, the first one that contains everything in cap K and x1 is in cap K, so this will be satisfied. But now let me translate what I wish to do. Okay, but let me do it like this. First note the following. Since K is totally bounded, K is bounded, and so there is some real number n, and x0 in K such that K is contained in the cap M ball about x0 with respect to rho. Moreover, script G has no finite subcovering for B rho M x0 intersection K, since that's simply cap K. Well, here, since this is the first set in my sequence, well, there is no preceding one. Well, the intersection with the preceding one being non-empty is not valid in here. Okay. Now we wish to construct a sequence of balls such that the nth ball that has radius cap m over 2 to the power n, it has a center which belongs to cap k, such that script G has no finite subcovering for the intersection of Bn with cap k, and Bn has a non-empty intersection with the previous ball, Bn minus 1. Then we'll show that the centers form a sequence, which is a Cauchy sequence. And then we'll use the limit of that to reach a contradiction. But here we have the first term, set P0 equal to the cap M ball about x naught. Now we'll proceed by contradiction. We will assume that we have, for some n, for a natural number, that we have constructed a sequence with the properties, I will write that in full, from B0 up to Bn minus 1. If we can now produce Bn, which satisfies the same conditions, then by induction it will follow that there is a sequence which satisfies all the three requested properties. Okay. So here, B0 intersection K, well, note that B0 is equal to B rho M over 2 to the power 0, this is just M, x naught, for some x naught in K, and script G has no finite subcovering for B0 intersection K. So this satisfies the two properties, but the third one is vacuously satisfied because there is no preceding term. Now assume that we have constructed for some natural number n from B0 up to Bn minus 1. Well, when n is 1, this will just be B naught, such that 1 for all k in 0 up to n minus 1, Bk is the m over 2 to the power k ball with respect to rho about xk for some xk in cap k. That was our first condition. At each step, we should have half the previous radius, and the center should be a member of cap k. Secondly, for all k in 0 up to n minus 1, G has no finite subcovering for Bk intersection cap k. Well, we have seen at the initial step of induction that holds. And thirdly, for all k in 1 to n minus 1, Bn intersection Bn minus 1, that's not empty. That also holds for B0 because, well, this becomes the empty set in that case. Okay? Okay. Now, having assumed this is our induction assumption, we will now produce some Bn such that Bn also satisfies all these three properties. Okay? Let's do that. What do we know? Well, we know that our set K is closed and totally bounded. Now we are seeking an epsilon ball where the radius will be cap m over 2 to the power n for Bn. But by total boundedness, we know for any epsilon positive, thus in particular when we take epsilon to be cap m over 2 to the power n, there are finitely many members in cap k such that the epsilon balls around those points, the union covers cap k. So, well, then one of them is a strong candidate to be Bn. Okay. Now set epsilon equal to m over 2 to the power n. That will be larger than 0. Since K is totally bounded, there is some finite non-empty subset E of K with, if I take the epsilon, that is the cap m over 2 to the power n balls, with respect to rho, well, about x's, when x is in E, this will cover K, just by definition of total boundedness. Well, we have in mind, well, can we choose some member from cap E to be xn? Well, it is clear that if I take any xn in cap E, that might not do, because I might not actually meet this condition. So let me first take the subset of cap E which meets this condition. Set F equal to the set of all x in E such that Bn minus 1 intersection B rho m over 2 to the power nx is non-empty. Well, will F be necessarily non-empty? Yes, because the collection of this that covers cap K. Is some portion of cap K in Bn minus 1? Well, in fact, an abundance of members of cap K are in Bn minus 1 because the assumption is that script G has no finite subcovering for the intersection of Bn minus 1 intersection cap K. Clearly, F is non-empty. Since Well, then, if I take just those members in this collection of epsilon balls, when X is in F, take the intersection of, well, the union or of each of them. Let me write it like this. Now, this will cover Bn minus 1 intersection K. Well, take anything in here. Well, since I take here from this collection everything which has a non-empty intersection with this, well, it will belong to some ball for some X in cap F, but it's in K, it will be in K again. Okay? But now, here you have this set such that script G has no finite subcovering for this set. Is it possible that script G has a finite subcovering for each of these finitely many sets? Well, if it had some such finite subcovering, we would collect those finite subcoverings, which would again a finite subcovering, but then that would be a finite subcovering for this set, but then that would be a finite subcovering for this set. Now, since script G has no finite subcovering for Bn minus 1 intersection K, and F is finite, script G, there is at least one member in here. Let me refer to that as Xn, such that script G has no finite subcovering for Bm over 2 to the power n with respect to rho Xn intersection K. Set Bn equal to just this cap m over 2 to the power n ball about Xn. It's of the required form, 1. Well, G has no finite subcovering for Bn intersection K, and we have chosen this actually Xn from F, so the intersection with the previous one, Bn minus 1, that's non-empty. Well, let me write that once more. In summary, Bn is equal to B rho m over 2 to the power n Xn for some Xn in K. Script G has no finite subcovering for Bn intersection K and Bn intersection Bn minus 1, that's non-empty. So by induction, it follows that we can construct the whole sequence. Because given n of them, we were able to produce the n plus first term such that all the three properties are satisfied. So let me write it here. Oh, I'm sorry. And then we'll give a break. I'm very sorry. So, by induction, we constructed a sequence Bn. Now here we have n in n0. This was n union 0, such that 1 for all n in n0, Bn is B rho m over 2 to the power n xn for some xn in k. 2, script g has no finite subcovering for Bn intersection k. This again for all n in n0. For Bn intersection k. And 3, this time for all n in n, Bn intersection Bn minus 1 is nothing. Well, let's have a break of 10 minutes. I'm sorry for the time.